Hi, in the previous video we answered the questions: what is a sampling distribution, what's the use of a sampling distribution, and then went on to prove some aspects of the sampling distribution of the sample mean when the x's are normally distributed. So what's left to do in this video is to kind of discuss what the sampling distribution is of the sample mean when x's are not normally distributed but we have a large sample, and then we're going to, related to that, we're going to look at the sampling distribution of the sample proportion, and we're going to do that for large samples. Okay. Sampling distribution of the sample mean when the x's are not normally distributed but we have large samples. Okay, so let's say my x's are, say, IID, with mean, say for each guy here, is mu for each of these i's, and say the variance are the same for each I, equal 1 to n. That's just shorthand for saying x1 to xn, right? But this time I've not stated that the x's must be normally distributed. But I can say this. Then for large n, put that, the distribution of the sample mean will be, now here is the key word, will be approximately normally distributed with mean mu and variance sigma square over n. Question is, why? I'm not going to do a proof of this. Why? Because usually why is what you want to know. It's because of something called, one of the two pillars of probability theory, and you've probably heard it in lectures, because of the central limit theorem. Now there are different kind of versions of the central limit theorem, but the gist of it is like this. The gist of it is that the sample mean is, in large samples, approximately normally distributed, irrespective of the distribution from which the x's came from. So the central limit theorem concerns distribution of x bar in large samples. So it concerns the distribution of x bar in large samples. And the key thing is here, key point, that the individual x's do not have to be normally distributed, as has been assumed to now. So it concerns the distribution of x bar in large samples, and specifically saying that they are approximately normal. And that's normal. And that key point is that x's do not have to originate from a normal distribution. I'm going to give you an example to finish off with, so don't worry about that. As I said, there are different versions of central limit theorem. This is the one that you're most likely to see, because the other versions basically relax this assumption. This assumption is like the most strictest assumptions you can have. So it's like when you're doing economics, when they start building a model, they assume kind of maybe things which are not reasonable to assume, but they make the strictest assumptions to simplify the analysis. is what's going on here as well. So there are different versions of the central limit theorem by relaxing IID. This thing about IID, there's another video that goes into depth, only 5 minutes or so, to explain what this means. Right, so I want to kind of show you how I can kind of use this now, using the following example. Another result that you actually need to know. A sampling distribution of the sample proportion in large samples. Sampling distribution of the sample proportion, let's denote it by p hat, because I think that's what most introductory texts use. Sampling distribution of the sample proportions in large samples. Okay. Well, why don't we just state the result first, and then we'll go and show it. In large samples, this will be normally distributed with mean true proportion and a variance of p times 1 minus p over n. And some of you may be familiar, let's write this on the side, this guy here, you might say like pq over n, right, where q is 1 over minus p. And now right here, this is approximately the case, because it's very easy to forget the fact that this is only approximately true, right? This is approximately in large samples. Now, in my first video, we said that once we have a sampling distribution, we can compute things like confidence intervals and hypothesis testing and so on. So since this is approximately normal, then our confidence intervals for proportion, the population proportion, will be an approximate one. That's a subtle point. Okay, how about if I said that this proof is pretty easy? We need to show 3 things. Show that the expected value of p hat is equal to p. We need to show that the variance of p hat is equal to p1 minus p over n. And we have to show that p hat is approximately normally distributed. This third one again I ain't going to do, because this one just follows from CLT. And an introductory course, you don't need to go anywhere near this proof, so it's just normally distributed. We have to show this and this one. Right. First thing. P hat. Oh, let me just... P hat. Now, p hat is the estimate of proportion, isn't it? How do you calculate proportion of something? It's like the number of events of interest that happen divided by number of possible events, isn't it? In other words, it's like the number, if I can say, of successes, i.e. the number of things that we're interested in, divided by total number of possible outcomes. Total number of outcomes. So let's denote this by x. Total. Let the number of successes, let's denote by capital X, and total number of outcomes n. Then this word success should give you a clue. X is the number of successes in here n number of trials. We could say it like this. So what does it mean about the distribution of x? It must mean that it's binomial, because remember that is what a binomial distribution does. It counts the number of models, the number of successes in n independent trials of something, where each trial has one of 2 outcomes. It's going to be success or no success, and say probability of success is p. Oops, I should say the prime to the np, right? So what we know is that the mean of a binomial without proof is np, and we know that the variance of a binomial is np times q, or 1 minus p. Therefore, we can say quickly that the expected value of my pi hat is going to be equal to the expected value of x over p from this here. Everything comes from just knowing this. Oops, sorry, that's an n. N comes out, you got the expected value of x, but we know that the expected value of x for a binomial is np times np. N's cancel, p. So that is this bit. Next, the variance. The variance of p hat is equal to the variance of x over n equals 1 over n squared times variance of x, and the variance of a binomial is np times 1 minus p. P minus p. One of those that goes, so it's p1 minus p over n, and that is in here. Okay, so that's the sampling distribution of the sample proportions in large samples. Hope that's been helpful. Thanks for watching.